Look closely at the heart of your computer, and you aren't just looking at a piece of hardware, you are looking at one of the most densely populated cities on Earth. This is the motherboard, a complex, multi-layered labyrinth where billions of electrons commute at nearly the speed of light. Every millisecond, data flows through veins of copper thinner than a human hair, connecting the massive brain of the CPU to the lightning-fast memory of the RAM. But this technological metropolis isn't built with bricks and mortar. It is grown and etched through a process of extreme precision, where a single speck of dust can cause a catastrophic short circuit. Today, we go beneath the surface of the green and black substrate to witness the birth of a printed circuit board. From raw fiberglass sheets to a finished masterpiece of electrical engineering, we explore how we print the City of Electrons. It is a journey of chemical baths, ultraviolet light, and robotic precision that pushes the limits of what modern manufacturing can achieve. Welcome to the anatomy of the motherboard. Every great city needs a foundation, and for a motherboard, that foundation is a material known as FR4. It begins as a woven cloth made of fine glass fibers, incredibly strong and, most importantly, an excellent electrical insulator. This glass cloth is soaked in a specially formulated epoxy resin, a sticky, honey-like substance that will eventually harden into a rigid board. This combination creates a pre-preg sheet. It is lightweight, heat-resistant, and won't expand or contract significantly when the computer gets hot. To provide the wiring for our city, ultra-thin foils of high-purity copper are bonded to both sides of this resin-soaked glass. Under massive pressure and high heat in a vacuum press, these layers are fused into a single solid core. At this stage, it looks like a simple sheet of metal, but hidden within its chemical bonds is the structural integrity required to support thousands of surface mount components. This is the blank canvas upon which the electrical architecture will be drawn. How do you draw thousands of lines with micron-level precision? You don't use a pen, you use light. The copper-clad board is coated with a light-sensitive film called a photoresist. This film acts like the film in an old-fashioned camera. Using a process called photolithography, a high-intensity ultraviolet light source shines through a glass mask or photo tool, which contains the intricate blueprints of the board's circuitry. Where the light hits the photoresist, the chemicals harden, locking the design of the traces into place. The areas shielded by the mask remain soft. The board is then submerged in a chemical developer that washes away the soft resist, leaving behind a blue-colored map of the future electrical paths. It is a delicate dance of chemistry and physics, ensuring that every lane of our electronic highway is perfectly aligned. Even a deviation of a few micrometers would mean the difference between a high-performance machine and a useless piece of scrap. Now, we must carve the city out of the copper. The board enters an etching chamber, where it is blasted with a powerful chemical solution, usually ferric chloride or cupric chloride. This acid is programmed to eat away only the exposed copper that isn't protected by the hardened blue photoresist. As the board moves through the spray, the unwanted copper dissolves into the liquid, leaving behind only the precise pathways we designed. Once the etching is complete, the protective blue film is stripped away, revealing the gleaming golden-brown copper traces underneath. We are left with a skeleton of electricity, a complex network of copper roads that represent a single layer of the motherboard. However, a modern motherboard isn't just one layer, it's a high-rise. Top-tier boards can have up to 12 or even 16 layers of these circuits, all stacked on top of each other and separated by insulating prepreg, creating a three-dimensional grid of data. A city can't function if its streets don't connect to the subway systems below. In a motherboard, these vertical connections are called vias. To create them, high-speed robotic drills, spinning at an incredible 200,000 rotations per minute, punch microscopic holes through the entire multi-layer stack. These holes are often smaller than a human hair, and the precision required is staggering. Because these holes are drilled through insulating glass and resin, they don't naturally conduct electricity. To fix this, the board undergoes electroless plating. A thin layer of copper is chemically deposited onto the inside walls of every single hole, creating a metallic tunnel that bridges the gap between the top, bottom, and internal layers. Now, signals can leap vertically through the board, allowing the CPU to talk to the back panel ports and the power delivery system simultaneously. It is the plumbing of the digital world, ensuring that no component is an island. While copper is a great conductor, it is also vulnerable. Left exposed to air, it would oxidize and corrode, and a single drop of stray liquid would cause a short circuit across the board. To prevent this, the board is coated in a solder mask. While we often think of motherboards as being green, modern high-end boards use deep blacks, reds, or even whites. This polymer layer covers everything except the pads where components will eventually be soldered. After the mask is cured in an oven, a silkscreen layer is applied. This is the white lettering and symbols you see on the board. It acts as a manual for the assembly robots and technicians, labeling where the CPU goes, which way the RAM should face, and the specific names of every capacitor and resistor. It is the final aesthetic touch that turns a raw slab of technology into a recognizable piece of computer hardware, the signage for our finished city. Now, the board is ready to be populated. This stage is dominated by pick-and-place machines, the fastest and most precise robots in the manufacturing world. First, a stainless steel stencil lays down a perfect layer of solder paste, a mixture of tiny solder balls and flux, onto the exposed pads. Then, the robots take over. These machine heads move so fast they are a literal blur to the human eye, often placing over 30,000 components per hour. They pick up microscopic resistors, capacitors, and complex integrated circuits and place them onto the solder paste with a tolerance of less than 0.03 millimeters. There is no room for error. If a component is tilted by even a fraction of a degree, the board could fail. This is the surface mount technology, or SMT phase, where the passive board becomes an active, thinking machine, ready to process the vast amounts of data the modern world demands. Currently, the thousands of components are only held in place by the stickiness of the solder paste. To make the connections permanent, the board must face a literal trial by fire, the reflow oven. This massive industrial furnace is divided into several temperature zones. As the board travels through, it is slowly heated to approximately 250 degrees Celsius, or nearly 500 degrees Fahrenheit. At this precise temperature, the solder paste melts, transforming from a dull gray paste into a liquid silver pool. Through the magic of surface tension, the molten solder pulls the components into perfect alignment with the copper pads. As the board moves into the cooling zone, the solder solidifies, creating a high-strength mechanical and electrical bond. This is the moment of truth where the silicon and the circuit board become one, finalized in a sea of molten metal. A single faulty solder joint among thousands can ruin the entire assembly. To ensure total reliability, every board must pass through the gauntlet of quality control. First is AOI, Automated Optical Inspection. High-resolution cameras scan the board from every angle, using AI algorithms to compare the finished product against the original design. It looks for missing components, tombstoning, where a resistor stands up on end, or solder bridges that could cause a short. For the most critical connections, like those under the CPU socket, X-ray machines are used to peer through the chips and inspect the hidden solder balls beneath. Finally, the board is powered on for in-circuit testing, where a bed of nails, literally thousands of tiny spring-loaded probes, touches specific points on the board to verify that every trace is carrying the correct voltage. Only when the board proves it can handle the electrical stress is it cleared for the consumer. What began as a simple sheet of glass and resin has been transformed into a masterpiece of modern engineering. The motherboard is a testament to our ability to organize chaos, to direct the flow of billions of electrons through a microscopic landscape of our own design. It is the unsung hero of the digital age, providing the backbone for everything from high-end gaming and AI research to the simple act of sending an email. Every trace, every via, and every solder joint is a result of decades of industrial evolution, a culmination of physics, chemistry, and robotics working in perfect harmony. The next time you power on your computer and see the flicker of the LEDs, remember the City of Electrons humming beneath the surface, a tiny, printed civilization that makes the modern world possible. This is how a motherboard is built, and it is a marvel of the machine age. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.